Let's finish up our example now by doing parts C and D. Part C says find the electric field at these 4 different places. You'll see that these 4 different places correspond to these 4 different regions that we already found. So we're just going to plug the numbers into our expressions we found here and find our answer. Then sketch the electric field. To do that, we'll look at the general expressions here and look at the relationships for the electric field in the distance. Okay, let's do part C first. I've preloaded a little bit. I've written down the 4 places where we're trying to find the field. I've written down 3 of the 4 equations we had for field. Now we'll just plug and chug our numbers. So the electric field at 3 centimeters is when we're inside the insulating cylinder. So it's the density, which is 3 times 10 to the minus 4 coulombs per meters cubed, times the position where we're trying to find the electric field, 0.03 meters, divided by 2 times epsilon naught, that's our permittivity of free space, 8.85 times 10 to the minus 12. And that gives us an electric field value equal to 5.08 times 10 to the 5 newtons per coulomb. That it's positive confirms for us that it points outwards. Okay, the next place we wanted to find the field was at 6 centimeters. That's in between the insulator and the conductor, so we'll use our equation there, which is density of the insulator times the radius of the insulator squared. The radius of the insulator was 5 centimeters. Got to work in meters here, so everything, all the units work out. Over 2 times epsilon naught and times that by 1 over the distance at which we're trying to find the field, which is 6 centimeters, which we put in meters, of course. That electric field is 7.06 times 10 to the 5 newtons per coulomb. So there's our electric field outside. It's positive, so radially outwards, which is what we said from before. Okay, the next bit is at 7.75 centimeters. That's in between the inner and outer radii of the conducting cylindrical shell. That means that our electric field is inside the conductor. It's equal to 0. And then last, we're outside of everything. So we'll fill in what we had for our expression for electric field. Lambda, our linear charge density on the conducting shell, plus density of the insulating cylinder. I think I'm going to have to write a little bit smaller to fit everything in. Times pi times radius of the insulating conductor squared. Okay, I'm just going to sacrifice a few sig figs here for space. That's all divided by 2 times pi times epsilon naught. For anybody who's wondering, you don't have to write in all these units as you do your calculations. I like to do it just for completeness sake, but if you leave it out and just put your units in at the end, that is okay. So our electric field, once we're outside of everything, is minus 3.41 times 10 to the 5 newtons per coulomb. We had said that the net charge outside was negative because, hang on, I think I scrambled that up. We said that the net charge of the whole thing is negative, therefore the electric field points inwards, and that is confirmed by what we see here. So it means it's inward. Okay, last we'd like to graph our electric field. So we're going to think about each of our equations and we're going to use those to help us make the graph. I've got my axes sketched out here. I'm going to put my electric field on the vertical. I'm going to put my distance from the center on the horizontal. And I'm going to consider 4 regions. Inside the insulator, between the insulator and the conductor, in the conductor and outside the conductor. When we're inside the insulator, we see that our electric field is proportional to R. That means our electric field is going to be linear. E proportional to R, because this is where we are inside insulator. Our maximum value will occur right here. That's at the surface of the insulator. That's where your electric field is equal to density times the radius of the insulator divided by 2 times epsilon naught. You can fill in that value if you wish. I don't think I will because it's going to clutter up my picture. For my next area between the insulator and the conductor, that expression gave my electric field as falling off as 1 over R. Be careful here when you draw your graph. Things that go to 1 over R, you're tempted to draw those going to 0. But this electric field would only go to 0 if R goes to infinity. R doesn't go to infinity. It only goes as far as the inner radius of the conductor. So that electric field doesn't go to 0. And the value of the electric field right here would be E equals our expression right here, but for R we fill in the inner radius of the conductor. Okay, so there's our electric field at that point. It's good to think about these values as you're drawing your graph, just to make sure you don't get mixed up and you don't put things going to 0 when they're not supposed to. Okay, next we're looking at the electric field inside the conductor. That 100% is equal to 0. So that gets us a horizontal line at 0. And next, we're going outside the whole thing. Now this is our expression. Okay, this one's interesting. It goes as 1 over R, so it's going to be a curve, but it's negative. So we start with some negative value, and as our R gets very, very big, our electric field is going to go to 0. So we're going to start at some negative value, and we're going to curve towards 0. So for this part, as R gets large, E tends towards small. For this point right here, our electric field is going to be this number right here times 1 over the radius of the outer surface of the conductor. So we're filling in R equals R0. And you can find that number if you wish. Okay, so there's a nice looking graph of our system. It's kind of complicated, but you can get to it as long as you work step by step.